Section 3.4. We take a closer look at the sign test. Generally, when we have larger samples, we have greater power, right, of the test. Larger samples gives a shorter, or we say smaller range of the confidence interval. So for sign tests, we only have a need for independence and identical distribution. So if we're doing sign tests on medians, we generally have to do larger samples and then the Wilcoxon or t-test. We need only independence identical distributions for a sign test. We don't need symmetry, and we don't even need continuity. So we need less assumptions. We could have a gap in the values, talking about continuity. We just simply remove a group from the value set for whatever reason, or we may have definitive jumps in our data, not giving us continuity. For example, we could ask people their shoe sizes, and they are all incremental jumps. But for skewed distributions, we have to take care of that a median isn't a mean. So a sign test is different. Let's look at an example. Example 3.7. We have two subsets, two samples. The percent water content for selected quadrants. By quadrants, we mean, and these are the data, for example, we skipped in last lecture. So by quadrants, we mean areas of dirt. We go and want to see how much water there is in the ground. So we have samples of our selected quadrants, sample 1 and sample 2, and we want to test if theta, the median, equals 0 versus theta doesn't equal 0. So this is two-sided. We have two different samples. We're not testing they are different than each other, but we still use them as a single sample problem and test them against the our hypothesized population median. Test each of them one by one without comparing them. So in the example 3.2, which we skipped last lecture, we associated a plus sign for values greater than 9. Under the null hypothesis, a number of plus signs of a binomial with n is equal to 10, and p, the probability of each trial, is equal to 0.5 for the first, and binomial 20, 0.5, n equals 20, p still 0.5 for the second sample, two-tail. And for the first sample, we only have, let's see the sample data. For the first sample, we only have two values exceeding 9, which is 1.9 slightly exceeds 9, and 15.1 exceeds 9. So we have two plus signs. So probability for two-sided is 0.109. And which is what the table in the textbook gives, right? Remember the table of the binomial distribution to get each value result, we use that table. So for the second sample, we have 3 values greater than 9, right? Second sample is here. We have 3 of them exceeding 9. And then there's no and the probability of 3 or less is relatively easy to calculate. We just accumulate their probabilities, right? And so using the first sample, we fail to reject the null because p is large. Using the second sample, we need to reject the null because p value is smaller than 0.05. So since we have two tails, there's no priori reason to confine alternatives. The power of a test increases as the sample size increases. For binomial, we have plenty of ways to calculate probabilities, right? I introduced a way to use R in the homework one review video, and also we can use the tables, and also we can use Excel. So what is the sign if data equals theta? So we'll drop those points from the data that give us a bias towards rejecting the null. If we drop them, we'll reject more likely because we'll get more extreme than our data actually is. There is some theory that we could just flip a coin and then make that our data. It's actually theoretically correct to do that. However, you actually have to go and describe your results as repeatable to other people who are checking your work. And we could make the selection of the sign to be more conservative to create a large p-value if we want to avoid rejecting the null. So either way, we can get rid of some biased data that we define them as biased data. So confidence intervals. Example 3.8. There's a sign test with samples to determine exact confidence intervals. We could seek all values of the population and see what would be rejected when alpha is 0.05. So there's a procedure for doing that on a sign test. And then it's just that of using sort of the equivalence of the rejection rule, same thing as the p-value, and the confidence interval. So same thing. The procedure there of getting the confidence interval is a bit more detailed, but it's similar to what's done in section 1.4. So I'll skip the detail of this part. And in exact 97.84 confidence interval is that second is that the 9.1. That's the confidence interval of this CI. And then for the second, it's 95.86. It's closer to 95%, right? So the more observations we get in the sample, the more closer we can get to the exact confidence level. And it's important to conclude that the sample of 10 gives us broader confidence intervals, but also a higher confidence level. Or if it's a lower confidence level, it's also that's a confidence level lower than 95%, but it's still not exact 95%, right? But even with a higher confidence level, with a higher confidence level, the range is wider, is broader. Of course, because the sample size is small, and we can't match up the median, the numbers as closely with that what we desire, and close to the exact values of the confidence level. So the same median is appropriate. We make no assumptions about symmetry. For example, these are 7.65 and 8 for the two values, the median and mean. If we don't have symmetric data, we can still talk about medians responsibly, right? A lot of times we have things that clearly aren't symmetric in data sets, things like household income, because the household income are bounded in 0. There's no negative household income, right? Although I suppose there are some households that have negative net income when they have loans, students' loan, they actually lose money over years, but we still bound the household income as 0 as the minimum. So that is a way that we get skewed data. So increasing the sample size shortens the confidence interval with the same confidence level. We sometimes have skew with a long tail. This is common. Skewness makes normal theory like t-distributions or confidence intervals inappropriate. But when we use sign test, it's not that robust to long tails. So exploratory data analysis, EDA. In other words, EDA is what we do when we don't really necessarily want to play around with hypothesis tests or inferences using the numbers and tables. We simply visualize them. So more often just called descriptive statistics. One of the EDA tools might be useful in this case is box plot. So for sample 2, it declares 2 outliers based on the software packages rule of how to rule out outliers. Every software may have different rules, but they all rule out some outliers based on their rules. Sorry. So somebody maybe got too close to a pond or creek, or too close to a home, who just introduce their rainwater out into the particular land area. Therefore, they get a very high water content from those soil. Those may be the reason. So based on this EDA, we need to connect the context of this problem and get some possible reasons and have some further investigation of these outliers. So comments, 5 difficulty of observations equal to hypothesis median does not arise, but if it did, so we didn't in this thing get numbers too close, but it is possible to have a sign test. So tables are available. Software packages to calculate exact confidence intervals are available. Many programs can set confidence intervals similar to arbitrary values for T and similar confidence intervals for exact comparisons to nonparametric values. So computationally, sign tests usually work out pretty well, but with less assumptions. Example 3.9 is like example 3.8, but only applied to the sentence data of the example we used in data we used in example 3.6. So we have 108 word sentence, which may be an outlier, and we want to get a binomial confidence interval. So we actually get a shorter confidence interval with binomials. We did with Wilcoxon. Well, we have an asymmetry in the problem, a long tail, and that makes a difference. So when we have asymmetric data, a sign test actually performs a lot better versus the traditional t-test. So asymptotic approximation of this problem falls from the normal approximation to the binomial when p equals 0.5. If s equals to the number of success, for binomial, this is the mean, right? NP. And this is the standard deviation, the population standard deviation. So we can get a z value for every s. And then we use continuity correction to correct s. Just the idea that our continuous value sometimes take up. If we were to draw the histogram, we wouldn't get a continuous number. We're getting a center point. So we want to actually take the whole square, the whole rectangular histogram. So we could add these continuity corrections as this. and still get a pretty simple asymptotic result for that sign test. So with these asymptotic results, we actually get simplified computations, much more than the we might imagine, because we always can look up values, probabilities, the find z from a z table. So asymptotic, of course, is for larger sample size, when the normal approximation make more sense. So section 3.5, the use of alternative scores. Use raw data permutation tests, also called a Pitman test. We skip this, at least for this week. We will skip example 310 this time. So normal scores. Normal scores are not kind of a cute idea. Let's take this assumption. We love z-table. We want to use it as much as we can. We would just take our data and make it work like it's normal, but actually maybe it's just not normal. How to verify whether a data set is normal? We can use QQ plot, right? Probability plot. But suppose even when we use the QQ plot, sometimes the p-value is closer to 0.05. Then we just suppose we can use it. We can use the normal approximation. So we could use our z-table in that case. So we can go take our quantiles, our proportions in the center of the z-table and read to the edges. And then that is when we get the phi z, and look for z, the backward thing, right? Get z values for all of our values. If we put our data in ranks 1 through 5, so we can get quantiles like this, right? 1, 6, 2, 6, until 5, 6. So in R, this is the prompt sign. This one, Q norm from 1, column 5, and divided altogether in 6. Then this is the quantile, the z value. So this is actually the whole sequence, and then it does the Q norm format. It's called van der Weyden score. Wilcoxon work better, so we can also have other scores. So this is a supplementary or an alternative of the Wilcoxon. And then there are things we need to do with censored data, right? And they mentioned there's vast literature for censored data because censored data sets are more common in reality. Especially this happens a lot in pharmaceutical testing. We want to report the results where some of the people are still alive, so we don't have their death age. Therefore, the data is censored. This is a good thing, but it causes some trouble in statistics. We have other scores for other distributions, such as Savage scores, and that's for exponential distribution, or we sometimes call it exponential scores. So Savage is actually a man's name. All right, comparing tests and robustness. It's been done in less detail than in other discussions, but we have some stuff about testing robustness. But for right now, let's just roughly look at some. With the data sets, the 2 samples we use in example 3.7 and also 3.2 maybe. So there are some comparisons of the t-test, Wilcoxon, sign test, and Pitman. So t-test, we get the exact p-values using the data sets, and also we get the asymptotic z p-values using the normal distribution to do the approximation. So here are the comparisons of these 4 tests with both sample 1 and sample 2. So because we have asymptotic data and some extreme values, the t-tests just blow up. They're not really useful. That's why we introduce nonparametric methods, right? So then the asymptotic values for pigment test don't look too good, right? Why we say it's not too good, because it's a very large p-value. We fail to reject the null. However, when we use Wilcoxon sign test, the p-value is rather small. We may make different decisions if we use different methods. And so for Wilcoxon test, the asymptotic result and the exact values are practically the same, right? I mean, they are not same, but with regard to making decisions whether we reject the null, they actually fall into the same region as critical region or non-critical region, right? So therefore, that means for Wilcoxon, we don't need to trouble ourselves to calculate exact p-values. We can just use asymptotic methods to use z-tables to get p-values. That save us a lot of computation power, right? So in other words, just through the calculation of the z-table, so we can make decisions upon the null. Regarding sign test, the results come different for sample 1, but because if it's a small sample size, when sample size is small, the asymptotic result may not make any sense. But for when sample size is 20, the result is more similar, right? So, skip it. Okay. So example 3.12. You can read if you are curious, or if you like more details on normal approximation. But we have introduced a normal approximation in statistics in SPC course, and also it's quite basic. It's like a review. If you want to read it, we'll just skip it now. So then let's look at example 3.13. Suppose we have the data from example 3.2. Again, the 2 samples. No, not the 2 samples. The data from 3.2. Yeah, this sample. So we can omit a few values and then replacing them with 2 different values, which means we want to make some extreme observation even more extreme, such as 25. It's a extreme observation because it's the largest one. And now we want to replace it by 35, and then replace it by 65 to see if this kind of outliers actually affect our test result. Again, using t-test, Wilcoxon, and binomial. Let's see the difference. So our confidence intervals for t-test blow up pretty radically on the 95%, right? And they shift quite a bit to the right because of this extreme 35, right? Larger than 25, so shift right. And then although it isn't clear which test will work the best with those modified data set, we can observe that for t-test, the outliers make a big difference to the results. For Wilcoxon, the effect is these 3 are okay. but for this one, it's skewed to the right. So if we change we use another data set, another sample, these observations here, which is better, which is worse, may different. That means for different data sets with different methods, they may give us totally different results. Generally, we conclude Wilcoxon is more robust to outliers, but still there are some occasional exceptionals. We need to look at them and compare them. Maybe not for each time, but we need to make sure we know what we're doing. And some discussions of the fields of application, let's go through some of them. The fields of application where we can do statistics using the methods in chapter 3. So we'll look some examples. Motor policy claims paid by British Inference in 2005 is 1,570 pounds. But we would want to look at 2006. So this is an old textbook with old data set. Therefore, we have very old data and story. But anyway, it doesn't matter. So we want to test the median to predict the 2006. In the random sample of 25 is taken. So we could see a sign test. We could use a sign test to create a confidence interval and to see if we do have this level of insurance claims on coverage, on average. So, and second field, the medical blood pressure change after exercise program. So you also want to check resting blood pressure after taking a few exercise. So we can use the Wilcoxon and sign test. More fields and nearing medium noise level under the flat path to an airport, testing a modified aircraft engine, noise out of an aircraft engine, how it affects things on the ground. It's pretty hard to model theoretically because there are a lot of factors may impact the results. But the factors that we can control and analyze the correlation between the noise and the engine is quite only a few, right? So, but kind of easy to measure this, right? Although we may not model it practically, right? So if you would want to do that randomly, it's easy to measure. And because the planes don't come in exact the same positions and heights and angles and speeds, it's maybe incomparable. But for any data, although the data sets may be not quite clean or useful, we still can do some tests. It's just the result may not that interpretable. So another field, biology, have some insights into the heartbeat rates for female monkeys of one species and 2 little cats. So for all these problems, we can use Wilcoxon test to detect a shift, the location of the median, or get confidence intervals to cover a certain range. Among those range, there would be median inside that range. So, and there are more application fields, very interesting. So, in summary, what did we learn in chapter 3, Wilcoxon signed rank test? So we went through that, and we also used Walsh averages to get confidence intervals. We can just use the original data and the assigned rank to get the confidence intervals, but Walsh averages give us a better exploration of the values between neighboring observations. So that's why we use it. And then we talked more about the sign test. And we sort of just talked about a Pitman test in our comparisons, but we didn't expand how to perform one and the exact details. So we talked about normal scores, but didn't focus quite on it. And that's all for this chapter. And then that's all for this week.